Hey there, class. We're here today. We're going to look at example 1 from our notes. And this is a circular motion type problem. So we basically are trying to find the minimum radius of an airplane. Okay, so this minimum radius, this is our find quantity. We have an airplane flying at 300 meters per second, so that's a velocity. Can make a U-turn if its centripetal acceleration is 4 Gs. I do note here the units are in Gs. We would need to change this into an MKS system, so there is going to need to be some kind of conversion into meters per second squared. We have a pilot sitting in the plane, and he has a mass of 75 kilograms. So we want to know, what force does this pilot feel? So again, a second thing to solve for is the force that's felt by this pilot. Okay, so in the reality here, the pilot and the plane are both moving together. So since we are going to look at what the pilot is feeling in the end, I just drew a net force diagram of our pilot. So basically, there's this circle that it travels in. The net force here is directed towards the center because, again, we know that this is undergoing a centripetal acceleration of 4 Gs, traveling at 300 meters per second around this. So again, we're trying to find this radius, and we're going to try to find this net force, or the force that's causing the centripetal acceleration. So once again, we summarize what we know, what we're trying to find, making a conversion here for the acceleration, of course, knowing that 1 G is equal to 9.8 meters per second squared. All right, let's come up with a strategy, how we might go about this, and we'll go ahead and implement it and see what we get. My strategy is going to be relatively straightforward here. We do know the centripetal acceleration, and there is an equation for that. It's v squared over r. We, of course, know the centripetal acceleration. We know the velocity or the speed, and we're going to basically solve for this. So basically, I'm going to isolate the r, so I'm going to solve for r. And algebraically, if I actually do that, what I'm going to end up with is r equals v squared over ac. All right, let's go over and let's go ahead and actually implement that. So basically r equals v squared, that was 300 meters per second, and that's over AC, which I want to say was 39.2. I'm going to go back and check it just real quick before I put the wrong number. So I did double check that, and we do have 39.2 meters per second squared. So I want to go ahead and calculate, bring up my calculator here. We're going to take 300 times 300 and divide that by 39.2, and we end up with, what do we have there? About 2,296, let's say, 2,296. So that would be 2,296. And of course, this is in meters per second on the top, and it's meters per second squared on the bottom. So my units for this would be meters. If we did convert this into something a little bigger unit-wise, it's going to be about 2.3. So it's approximately equal to 2.3 kilometers. And that sounds reasonable for a plane. You figure something that's traveling at 300 meters per second, knowing that the speed of sound is 343 meters per second. Okay, so the speed of sound is that we're having something here traveling, roughly 85% the speed of sound. So having a relatively large kilometer radius does make sense in this case. Okay, next up was the force that's experienced by the pilot, and this is, again, a relatively straightforward calculation. We know we have Newton's second law, which, again, our goal here is to find the net force, or the force that's acting on this pilot. We know his mass, and we just calculated the acceleration that occurs. We're mainly concerned about the magnitude, so I'm not really worried about the vector nature of these quantities. So I'm just going to go over here and we're going to substitute in some numbers. All right, so we are solving for the net force. The mass was 75.0 kilograms, and we know the acceleration is going to be 39.2 meters per second squared. Once again, let's bring our calculator up. And I'm covering up my numbers, so let me uncover them. 75 times 39.2. And it looks like we get about 2,940. 2,940. Let me go out here. All right. So that's about 2,000. I already forget the number. Let me go back and look. 2,295. That's, I think, my other answer. Hold on. Okay, so I did go back and find the calculation where I did it, and it was 2,940 newtons of force that the pilot feels. So again, if you consider the pilot who's undergoing 4Gs, that's a relatively large acceleration, and so that's going to make this pilot feel 4 times heavier than what they actually feel just standing here on Earth. So again, considering a normal person is probably somewhere around, an average person would be somewhere around like 800 newtons or so. You can see that this number kind of makes sense. It's about 4 times as much. So again, it's within the ballpark of what we might expect.